This next differential equation is a homogeneous higher order differential equation which can be solved using an equivalent auxiliary equation and solving for the roots. Here, it is stated that the roots are imaginary and there are some of the imaginary roots that are repeated or has multiplicity more than 1. Then if we have verified this, then we need to show the general solution in a form intended for this type of situation, because we have 4 situations. The first one, we have a general solution for distinct real roots where all roots are real and they are different from one another. We also have another general solution if some of the real roots have multiplicity. Then we also have a situation where our roots are imaginary. In this case, the last one, some of the imaginary roots has multiplicity. Our given here is already expressed in an equation using a differential operator d. Hence, let's move to the creation of the auxiliary equation where we use m, and it would be in this form: m to the power of 6 plus 9m to the power of 4 plus 24 m to the power, or m squared rather, plus 16 is equal to 0. Now here we are to solve for the roots of this given equation, but since the highest degree is 6, we are expecting 6 roots, and there might be some problems as we use the rational root or the rational zero theorem, because some roots are claimed to be imaginary. What we could do here is simple intuition, at the same time representation, talking about this. If we are going to let k be equal to m squared, instead of m to the power of 6, we'll be making an equation which is easier to look at, and that would be this form. You will have m cubed you will have k cubed, because your m to the power of 6 has a 3m squareds, okay? Then plus 9k squared plus 24k plus 16 equal to 0. Let's use this, which is easier to look at than the first one. Here, again, you can use your different styles of factoring this, but let us assume some values. What if k is equal to 1? Substitute that here, and if it returns 0, then k equal to 1 is a root of this given situation. Okay? But of course, you will try that. You will have 1 cubed is 1, plus 9 times 1 squared is 1, plus 24 times 1, and plus 16. As you can see, they're all positive. Definitely, it will not be equal to 0. So let's try another value. Instead of 2 and instead of fractions, how about we try negative 1? Let's try. So we have here the cube of negative 1 is negative 1, plus 9 times the square of negative 1 is positive, plus 24 times negative 1, plus 16 equal to 0. Let's try. Negative 1, you have positive 9, you have negative 24, you have positive 16. This is 25, this is also negative 25, and yes, it's equal to 0. Hence, the first root is negative 1. But this is not the root that we're talking about here, because this is just the root of the this equation where we let k is equal to m squared. We will return to that later. Okay, let's stick with this first here. Let's solve first all the values of k for this time, and then later on substitute m squared to all of the situations. So once we had this, let's use here what you call this one, the static division. So we have 1k squared, k cubed, 9k squared, 24k, and then 16, you have here minus 1. So that we can trim it down to another quadratic equation. So you have here 1 times 1 is negative 1. Then you have here 8, negative 8, that's 16, negative 16. Once you reach 0 remainder, that means this is really correct. And we have the value we have assumed earlier as one of the roots for k is correct. Here, you will have k squared plus 8k plus 16 is equal to 0. And this time, a quadratic equation. You can use the quadratic formula, you can use the factoring, or in this case, we know that this is a perfect square trinomial multiplying a binomial expression with itself. You will have, this is a perfect square trinomial because you have a perfect square 16, perfect square k squared, and the middle term is twice the square root of k squared k, and the square root of 16, which is 4. That's 8k. So this is a perfect square trinomial. Hence, we'll have k plus 4. The square root of first term is k. The square root of the last term is 4. Use the sign of the middle term. So you have your k plus 4 as well equal to 0. So with this here, earlier, there's also k plus 1. That's another factor. So bottom line, for this item here, or this representation where k is equal to m squared, that's k cubed plus 9k squared plus 24k plus 16. The factors are k plus 1. Okay. You will have k plus 4 and k plus 4 equal to 0. Before we solve the values of k, we can now return to the value of k, or the representation for k, which is m squared, because it's the m that we're solving for. Because here we only have 3 k's, and since it's m to the power of 6, the original auxiliary equation here, we're expecting 6 roots. So this time, we will substitute m squared plus 1, m squared plus 4, m squared plus 4 equal to 0. As you can see, there is already a repetition here, and hence we have verified this first claim repetition. As for imaginary, it can be proven as to this. Now first, m squared plus 1 equal to 0, m squared is equal to negative 1. Okay, so m is equal to plus minus square root of 1, negative 1 rather, m is equal to plus minus I. We have imaginary roots now. But for this alone, we cannot say that it's repeated because you only have this representation of imaginary roots. It will follow on the second. M squared plus 4 equal to 0. M squared plus 4 is equal to 0. No need to do this because it's just the same as that. Hence repetition. M squared is equal to minus 4. Square root of both sides, you will have plus minus square root of negative 4. M is equal to plus minus, you will have 2i. And again, this is also the same here, plus minus 2i. So there is a repetition on the roots. Now, please be cautious with this. Since our solution, our roots now has an imaginary that is not repeated and imaginary roots that have been repeated, we are going to combine the third and the fourth types of general solution. The third form of a general solution, once we have imaginary roots which are not repeated, can be expressed in this manner. Y is equal to e to the power of ax times c sub 1 cosine bx plus c sub 2 sine of bx, where our a and b can be taken from the root, which is a plus minus bi. Okay, this is just for the imaginary. We have many examples for that previously. Now for the repetition, here comes the interesting part, as this will look into like this. Y is equal to e to the power of ax c sub 1 cosine bx plus c sub 2 sine bx plus there x e to the power of ax, that has been repeated, c sub 3 now cosine bx same b plus sine of c sub 4 sine of bx plus dot until you reach, if there are the multiplicity is more than 2, it's n, so you will have here x, you have here n minus 1 e to the power of same ax times c sub n plus 1 cosine of bx plus c sub n, sorry for that, sine of bx. But since our multiplicity is just 2, so we'll just end up here. No need to extend it further. Now, I hope that my spaces here are enough, but if it's not, then we are going to move to the next page. But it will look like this. Take note that our a on the first set of roots, which is not repeated, a is 0 and b is 1. That's 1i. Here, a is 0, but b is 2i, so that's 2. So we can combine them now in this form. Okay, y is equal to, please bear with me because I'm going to jump immediately to the result, as you have e to the power of 0x, that's your a, that's just equal to 1. Okay, so that would mean this is equal to 1. No need to have that multiplier because of a 0 exponent. Hence, you will have c sub 1 cosine of your 1x plus c sub 2 sine of your 1x. Take out, okay? This is already equal to 1 because your a is 0. And then we don't need the parenthesis. Now, going to this portion, plus, again, e to the power of 0x, because a here is 0, that's still equal to 1, so no need for that multiplier. Okay? That's why you really need to look into the possibilities of this. And you will have here, instead of c sub 1, we'll be using c sub 3 because c sub 1 has already been used here. But no worries, remove this again. No need for parentheses for that. Okay? So, plus c sub 3 now, cosine of 2x, because that's bx now, plus c sub 4 sine of 2x. Now, here comes repetition. Plus x e to the power of 0x. Again, it's just equal to 1. No need to do that. Now, this is now a multiplier of this next set. C sub 5 cosine of 2x plus c sub 6 sine of 2x. Close. We have 6 different terms. 1, 2, 3, 4. Of course, this one here can be distributed 5 and 6. So this is now the solution. As you can see, it now combines the possibility of imaginary roots which are not repeated and imaginary roots with multiplicity. How much more if we also have, what do you call this one? Real roots that are distinct and repetition. So there's a lot of changes now. But for this is now the final result for this given differential equation. Thank you very much for watching.